Am
right.
I audible?
Then, yes, you are.
All right. How about the screen? Is it okay?
Yeah, it's okay.
Okay.
You got 10 minutes.
All right. Thank you so much.
Sure.
Okay. I'm Migbar from University of Botswana. I'm going to present the topic numerical simulation of coupled thermoelectric phenomena using peridynamic theory. Okay, this is our outline. First, I'm going to talk about introduction, and then I'm going to say a few points about the classical continuum theory drawbacks, and then I'll touch a little bit on the review of this peridynamic theory and its application, and then followed by peridynamic formulation coined to coupled thermoelectric phenomena. And then I'm going to present a couple of examples, results, discussions, and then conclusions. All right. So to start with, I think this peridynamic theory directly, it's better to start with finite element modeling. In finite element modeling, we are going to discretize a domain into a number of pieces called elements so that we can solve our problem based on the differential equations. These are some of the examples here. Finite element has got a number of applications like in aircraft industry, automobile industry, etc., crashworthiness, fracture mechanics, and so on. So the main idea behind this peridynamic theory is in dealing with discontinuities from nanoscale to macro scale. This one is the nano, and this is the macro scale. Some of the shortcomings of the classical continuum theory is the governing equations are partial differential equation based, so they are not convenient in dealing with discontinuities like cracked tips, maybe faces, and so on, because these things are, mathematically speaking, they are singular. Theoretically, they will have infinite. In case of solid mechanics, we are going to experience infinite stress, infinite heat and electric flux, etc., etc. So to capture such type of discontinuities, we need to have external criteria so that we can capture these discontinuities. So to overcome such type of difficulties or drawbacks of continuum mechanics, Stuart Sealing from Sanya National Laboratory devised a new, of course, it's a relatively new technique called peridynamic theory. This peridynamic theory is some kind of meshless kind of theory, so that it has got its own beauty. So I'm going to say a few points about this peridynamic theory. This theory, it is a non-local theory. So the theory uses integral differential equations in place of partial differential equation, which is in case of classical continuum mechanics theory. So we don't have any partial derivatives. Therefore, these equations can be directly applied whether we have discontinuities or not. We can just make use of these integral equations. Okay, we don't need any external criteria like the continuum mechanics based theory. The other interesting feature of this peridynamic theory is it can capture a number of multiple cracks, okay, discontinuities, and so on. Well, this is if you have a continuous system, and if there is any discontinuity, as I said before, this non-local theory captures, interestingly, using this mesh-free method. We call them material points. Okay, this is the principle of thermoelectric generator. Just simply, if we have a temperature difference, this temperature difference is going to be converted into electricity using this P and N junction type of thermoelectric generator. Okay, when this device is in operation, it's going to be subjected to a high temperature difference. So there will be cyclic type of thermal stress. That is going to be our point of interest in this paper. So in peridynamics, the theory, if there is a discontinuity like this, the green line, okay, it's going to break theoretically the bond between the particles. The blue ones are, we can assume they are particles. They are just joined together by kind of link. We call it technically bond. Okay, if there is a crack, that bond is going to be broken. So when it's broken, definitely the load is going to be moved to the neighboring bonds. Like that, we are going to solve the problem using peridynamic theory. So this is just a comparing and contrasting local theory versus non-local theory. In local theory, the particle is interacting with its immediate neighborhood. So we are going to use the equation of motion, the usual continuum mechanics equation of motion here, which is partial differential equation or divergence based. But in case of non-local theory, this particle is going to interact beyond its neighborhood. Okay, so we have what we call it a horizon HI. So this particle I is going to interact with all the families inside this horizon, and the equation of motion is going to be rather integral equation. So this is in case of one dimension, this particle I interacts with the three neighboring particles. So our horizon radius is going to be 3. If it is in 2D, we are going to project it in the y direction. And then if we have 3D, we can extrude it to the one perpendicular to the slide. Okay, these are some of the applications of peridynamic theory. It has got a number of applications, but these are some of them. In case of damage and fracture modeling, elastic deformation in solids, in case of brittle fracture, corrosion modeling, damage in composite materials, crack initiation and propagation, diffusion in case of heat and moisture, etc., etc. So the main target of this presentation is just to present some of the results we have using peridynamic theory. We analyzed a couple thermoelectric phenomena. This is the expression we have, the heat conduction equation and heat equilibrium equation of this mathematical expression shows the coupled thermoelectric equation in case of heat conduction. And this one is the equilibrium equation in case of a coupled thermoelectric expression. Here phi stands for potential, electric potential, T is a temperature. Here C stands for the bond that connects the two particles, let's say A and B, and beta is the Peltier effect, kappa thermal conductivity, sigma electrical conduction coefficient, and S is a Seebeck coefficient. So as I said before, electric is going to be generated using this temperature difference in case of thermoelectric materials. So this is in case of electric conduction. We have seen in the previous slide, which is thermal conduction. This one is electric conduction and its equilibrium equation. So the above equations are solved. I'm going to demonstrate 2 or 3 examples to show. In the first example, the temperature and the electric potential distribution using peridynamic theory in case of 2-dimensional plate. Followed by, I'm going to present discontinuities in case of adiabatic and isothermal cracks. This is my domain.
You have 1 minute left.
Okay, thank you so much. This is in first example, we have this model. So we have different boundary conditions. We have 2 solutions. The first one is a peridynamic solution, and this one is a theoretical solution. As you could see here, they are in good agreement in case of temperature distribution. This is a distribution of potential. Again, they are in good agreement. In the second example, here we have a discontinuity, kind of T kind of discontinuity, which is right and left are insulated, and we give temperature difference in the top and the bottom. This is the result, which is compared with the finite element result. Again, it's in good agreement. And then the other one is in case of isothermal crack, and we have a very good agreement in this, the results are in good agreement. These are some of the conclusions, and these are some of the reference. Thank you very much for your attention. If you have any questions, you may drop on